Hello guys, welcome back. So here we have another question on communication systems from GATE EC 2022. The frequency response h of f of a linear time invariant system has magnitude as shown in the figure. So here they have given the magnitude and this is 1. Okay. Statement 1. The system is necessarily a pure delay system for inputs which are band limited to minus alpha less than or f less than or equal to alpha. And statement 2, they're saying for any White's and stationary input process with power spectral density xx of f, the output power spectral density xy of f obeys xy of f equal to xx of f for minus alpha less than equal to f less than equal to alpha. Which one of the following combinations is true? So we have statement 1 is correct, statement 2 is correct, and the other combination where it is incorrect, correct, incorrect, and incorrect. So let us visit each statement one by one. So first let us take statement 1. So say statement 1 is talking about pure delay system. So what is a pure delay system? If we give the input x of t, the output y of t should be delayed version of x of t, some t minus t naught. So in the frequency domain, how will this look? So your y of f will be nothing but e power minus j 2 pi f t naught into x of f, right? So your mod y of f, or if you just want to find your h of f, because your h of f is what we are talking about, right? So your h of f is y of f by x of f. So which is nothing but e power minus j 2 pi f naught t, f t naught. So now mod h of f is equal to 1. And what is your angle of h of f? Phase of h of f? Phase of h of f is equal to 2 pi f into t naught, and with the minus sign. So now let us go back and see what is given. We have given only the magnitude response, and magnitude response is 1 in this interval. So we are only concerned in the interval minus alpha less than or equal to f less than or equal to alpha. In this interval, what do we have? Mod h of f is equal to 1. This is tick. But for a pure delay system, the phase is also important. Without the phase, it will not be a pure delay system. I'll give an example for that also in a while. So is the phase equal to minus 2 pi f t naught? No, there is no information given about the phase. So then let us go back to the statement. What it says, the system is necessarily. Is it necessary for it to be a pure delay system? It is a pure delay system only if phase is also equal to this. But since no information is given about the phase, it is not necessarily a pure delay system. So this statement is incorrect. So now I'll give an example why phase is also important. Let's say your x of t is sine t plus sine 2t. Okay. Let's say your phase is h of f is some constant. Let's say it is pi by 2 for f greater than 0, minus pi by 2 for f less than 0. So this I'm saying because since sine t is a real function, it's since y of t also should be real, your h of f phase response should be a odd function. That is why I'm writing this way. So your y of t will then be sine of t plus pi by 2 plus sine 2t plus pi by 2. So this will be your output y of t. If you see, this I can't write it as x of t plus pi by 2. Why? What is x of t plus pi by 2? It is sine of t plus pi by 2 plus sine 2 into t plus pi by 2. Which means that it is sine t plus pi by 2 plus sine of 2t plus pi. So it means that as the frequency increases, the phase delay also is increasing. So as omega increases, your phase delay also should increase. And in what way? It should increase in a linear manner. So if you go back here, you can see The phase here is linearly proportional to your frequency f. So only in that case it will be a pure delay system. Otherwise it will be something like this. So this, if you see, it will not be a pure delay system, which means that your y of t is not a exactly shifted version of your time shifted version of your x of t. Okay, so this is with statement 1. So let us now take a look at the second statement. So statement 2. For any wide sense stationary input process. So what is a wide sense stationary input process? So stationary means something which is not changing over time. And wide sense stationary has two properties. So the first one is, so I'll write wide sense stationary. So the first one is its mean. So its mean does not change over time. It is same as x of t plus some tau. And this is constant. And it is independent of time. And the second one is its autocorrelation function. So Rx of t1 comma t2. Here again it is not depending on the absolute value of the times. It is only depending on the difference between these two times. So in other words, it depends only on the time difference between the points. So if a process satisfies these two properties, it is called as wide sense stationary. So when a wide sense stationary signal x of t is passed through a LTI system and we get the output y of t. So this output y of t is given as convolution of your impulse response of your LTI system with x of t. So in terms of power spectral density, it is xy of f is given as mod h of f whole square into sx of f. So this is what we get. And in our thing, we are interested in minus alpha less than f less than alpha. So in this region, your mod h of f is given as equal to 1. So which means that your xy of f is equal to xx of f. And this is what they have given in statement 2. For any wide sense stationary input process with power spectral density xx of f. So this is the input power spectral density. The output power spectral density xy of f obeys xy of f equal to xx of f for minus alpha less than equal to f less than equal to alpha. So we get the same thing. So statement 2 is correct. So we got that statement 1 is incorrect and statement 2 is correct. So the correct option is option C.